This is a second video on Chapter 42, the Fundamental Theorem of Calculus. And as I mentioned in the first video, there's a little bit of a play on words here because I've been calling my videos different parts, but yet Theorem 332 is the Fundamental Theorem of Calculus Part 2. Before you go on, you should look at definition 329, example 330, and note 331. I'm not going to talk about those in the video very much, but definition 329 is of an antiderivative. You should know what that is. So I would encourage you to pause the video at this point, pick up your notes, and study this part first, because the stuff I'm going to say later on depends on some of this material. So definition 329 is a definition of an antiderivative. Example 330 is some examples demonstrating that antiderivatives are not unique. Note 331, however, tells us antiderivatives are unique up to a constant. That is a corollary of the mean value theorem. And if you go back to the chapter on the mean value theorem, you will notice that that's mentioned, that if two functions have the same derivative, they differ by a constant. So theorem 332, the Fundamental Theorem of Calculus Part 2. You're going to like this one. So when we were looking at derivatives, and we calculated a derivative using the definition, so we took the limit as h goes to 0 of f of x plus h minus f of x divided by h, we did that for a while. Then we learned the power rule, and we learned some other rules that made taking derivatives of algebraic functions simpler. That's what the Fundamental Theorem of Calculus Part 2 is to us for integrals. So at this point, we won't have to rely solely on the definition of integral to calculate our integrals. We can use the Fundamental Theorem of Calculus Part 2, which says the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F of x is an antiderivative of f of x. So in other words, the derivative of capital F of x is f of x. So example 333, there are several examples. I'm going to do 3 of them. Parts A, B, and C are all similar. So I'll work through part B. We have an integral of a polynomial. Polynomials are easy to differentiate, and they're almost as easy to integrate. So differentiating, you just use the power rule all the way through. Integrating, you reverse the power rule all the way through. So we find an antiderivative of this third degree polynomial is this fourth degree polynomial. After you find the antiderivative, you substitute 3, then you substitute 1, then you subtract. The details of that arithmetic are in the notes, and so you should look at your notes as to where we ended up with the 30. Okay? When you're turning in your assignment, I will want you to show those details. So if you give me this example, or you give me this answer in your assignment, I will take off some points for not showing enough detail. So in other words, do as I say, not as I do. Or actually, do as I did in the notes and not as I'm doing in the video. So I've left off the details just to save recording time and to save board space. But the details are in your notes. Part D can be done in a couple of different ways. The thing about the absolute value function is we've never looked at a function whose derivative is the absolute value function. So we haven't ever found an antiderivative of absolute value of x. So what we're going to do is we're going to take advantage of the fact that the absolute value function is actually a piecewise defined function. It's defined differently from -1 to 0 as it is from 0 to 1. From 0 to 1, the absolute value of x is simply x. From -1 to 0, the absolute value of x is the opposite of x, so it's -1 times x. So we find an antiderivative of -x, which is -1/2 x squared. And if you want to, take the derivative to check your answer. So just use the power rule here. Take this derivative, we have -x. An antiderivative of x is 1/2 x squared. Again, check your answer by calculating this derivative. The derivative of 1/2 x squared is x. So for this part, we substitute 0, substitute -1, and subtract. When we substitute 0, we have 0. When we substitute -1, we have -1/2, and we subtract. So we have 0 minus -1/2, which is 1/2. Substitute 1, substitute 0, subtract. We substitute 1, we have 1/2. We substitute 0, we have 0. So we subtract and we have 1/2. So we have 1/2 plus 1/2, which is 1. Another way to do this is by the area under the curve. This is the graph of the absolute value function. And we have two triangles. The base of this triangle is 1. The height is also 1. So we use the formula 1/2 base times the height. So the area of this triangle is 1/2. The area of this triangle is 1/2. So the area under the curve is 1/2 plus 1/2, which is 1. And finally, we'll look at part E. We have the integral from 0 to pi of sine x dx. So we find an antiderivative of sine, which is negative cosine of x. That's because the derivative of cosine is negative sine. So -1 times cosine of x calculate this derivative of -1 times cosine of x, and you have sine of x. We'll check our answer. We'll substitute pi, we'll substitute 0, we'll subtract. Cosine of pi is -1, so that's where this -1 comes from. This negative sign is this one right here. So we have -1 times cosine of x. So we have -1 times cosine of pi, so we have -1 times -1. Then we subtract. That's the meaning of this symbol. We're going to subtract cosine of, or -1 times cosine of 0. Cosine of 0 is 1. So we have -1 times 1, that is this -1 right here, and this is a subtraction sign, goes along with the meaning of this symbol. So we have, at the end, we have 1 plus 1, which is 2. A very common mistake in integrating is making a sign error, S-I-G-N error. So be very careful with your positives and negatives.